Okay. So you are asking me what is hashing? Um, so the question is, why do we even want to hash? Okay. So let's say you have uh, uh, you have some data or you have some information uh, which you want to compress. Okay. And you want to compress it so that it less uh, it takes less space to represent that data. Okay. Just give me a second. Yeah, sorry. Yeah, so okay, so let me just write.
Is your health okay, sir?
Yeah, I'm okay. Thank you.
Okay, okay, okay. Then go ahead, sir.
Yeah, yeah, yeah. So typically in computer science, when do you want to hash something? So let's say you have. Uh, so let me just first explain the use of hashing in typical applications in computer science.
So
So
sorry to
let's say you
interrupt.
have.
I am
Uh,
only mathematic. I have only mathematical background. I am a mathematical faculty.
yeah.
I know anything about
Yes.
computer science.
Yeah, yeah.
Okay.
So I'll explain it in elementary terms
Yeah.
because hashing is not something that that someone who does pure mathematics would know about. So because this course is probability for computer science, that's why this course has some elements of what I would say uh, um, uh, enumerative combinatorics using techniques from probability. So
Both
hashing is
probability.
a yeah, it's enumerative combinatorics. I'll bring up a question towards the end, which
Okay.
is essentially a question of enumerative combinatorics, but a probabilistic method is applied over there. So hashing is in computer science and computer systems a very archetypal application of these things. It can be used to uh, understand the quality of various hashing schemes and so on. So the question is, what is hashing at the first place, and why do you even want to hash? So let's say you understand what is a string, right? A string is a you can think of a string as like a sequence of alphabet. Even. Okay. Um, S1 and S2. Okay. Now, if um, so you understand what a string is, right? A string
String is a
is a
sequence of,
sequence
I
of
think it's numbers.
alphabet. It's a sequence of numbers, or it's a sequence of alphabets, anything. So let's say you have an alphabet. So let's say A is an alphabet. So because you are from the math, so I can explain it a bit more formally. So you can think of an alphabet as a set of characters, basically. So let's say it's some set of characters, A1, A2, AN. Okay. So then you can think um of a string S as an element of cross product of A, um, where this indexing set is is all over the set of natural numbers. So essentially, um, a string is a finite number of, so it's a string. So a string is a string of elements uh, from this character set. So it's like some A1, some AI1, AI2, AIK. This is an example of a string. this is contained in this, right? And so so this is a so you will see that this is an infinite Cartesian product, but we don't deal with infinite strings. We deal with finite strings. So the way you represent finite strings is as follows. Um, you introduce in this character, so in this sequence of alphabets A1 to N, you introduce something called a null character or a dummy character. So you call it uh, phi, something like that. So phi is like a null character. Uh, so a string would then be represented as AI1, AI2 to AIK, and the remaining terms, because this is an infinite sequence, the remaining terms would be like 5, 5, 5, 5, 5, so. Okay. Um, so eventually all the terms in a string is 5. So this is just formalism. You understand what a string is. Like a string uh,
Sir.
is given an alphabet, it's a word. So strings are sometimes called words also. All the words of the English language are a are the strings. Are strings. So now let's take the example of words in the English language. You have 26 you have 26 alphabets, and think of all the possible strings you can make with those 26 alphabets. It's a huge number of strings that you can make a possible, you can make an infinite number of strings, right? But the total number of words in the English language is actually quite few, is actually quite less. Okay. Um, more than that, uh, uh, so even if we say something like consider all the words of the English language whose whose length is less than or equal to 50. Most words in the English language have length less than equal to 50, right? Um, but uh, if I ask you to construct a set of all possible strings of length less than equal to 50 with the letters from A to Z, there's a huge number of strings that you can form. But the number of words, the actual number of words in the English language is far fewer than that. Okay. So the first thing is sparsity. Uh, Sparsity means that the set of words in my dictionary is a subset of the set of all possible strings. Okay. So now you understand what I mean by this, right? Uh, do you understand what I mean by this?
No, sir.
You don't understand. Okay.
String I know.
No, no,
So
no.
the subsets of
So
the subsets of the
hmm.
strings are actually called sparsity.
No. So sparsity is a concept. Sparsity is a concept. So think about in this way. So okay. So let's take an example. So how many words? How many? Sorry, not words. How many strings? Uh, so your alphabet is the alphabets of the English language. So it's A to Z. And I ask you a question: how many strings of size less than or equal to 10 can be made, right? So the number of strings of this is the question I ask you. Okay, how many strings of size less than or equal to 10 can be made? So if you want to make a string of size k, uh, you can make it in 26 to the power k ways. Now k now k varies from 1 to 10. So the total number of
So this is number of
strings
ways
of
of
size less than
arranging
equal to
number
number
of
of
ways
ways of
of
arranging
arranging R
all
objects in which repetitions are allowed. That formula used?
repetitions are allowed. Yes, repetitions,
Yeah,
everything is
permutation,
allowed.
in permutation. Okay, thank you.
Yeah. So it's k equals to 1 to 10. So this is a huge number, right?
Yeah,
26 to the power 10 is it's a huge number.
yeah.
But how many words? But now consider the English language, okay? And consider the valid words of the English language. Not like a word like XXXXX is not a valid word, right? So think about this all possible valid words of the English language. So now let's write this. So let's call this quantity n, something like that. Now let's ask this: what are the uh, valid words of size less than equal to 10? Whatever this quantity is, if I call this n0, then n0 is much less than equal to n. That's clear, right? That's obvious, right? How many words are there in the English language of size less than equal to 10? It's very few. It's definitely orders of magnitude smaller than 26 to the power 20. Okay. Um, so this is what I call sparsity. So sparsity means that um, um, sparsity means that I can express it a bit more formally. Um, so um, I can define it in this way. So how can I define sparsity? How can we define sparsity? So let's say you have a probability space. So omega is a probability space, and so it's a measure space, and there is a measure mu assigned to it. Okay. Assume for now that that this space omega is finite. Okay. So then we can say that this probability space omega comma mu is sparse if the set of elements in omega with uh, probability with mu greater than 0 is few. Get my point? Let's take the
Okay,
example
okay,
of
little.
let's take this example. You have
Okay,
the
okay.
words of the English language n0, and then you have the set of all possible strings n. Okay. Now, what is the probability that a word like X, Y, Z, W comes up? 0. Okay. So, if you're reading, so if you consider, so if you want to assign a probability to all the words in the English language based on how frequently they occur in some text, then the probability of X, Y, Z, W occurring in any text is 0. It's not a valid word. So we can say that a probability space has this sparsity property if the probability measure is concentrated in a very small subset of this space. So um, so what this means is that formally there exists a subspace mu, um, not subspace or a subset. There exists a subset mu, which is a strictly smaller subset of omega,
Omega.
such
Okay.
that on on anything outside this set is 0. And this set, omega prime, is much, much smaller than omega. Okay. Now,
Okay.
what do we mean by much, much smaller? Uh, that itself, uh, that itself can be defined in different contexts. Okay. Um, if you understand, uh, if you understand, if you have some knowledge about analysis, if you know what is meant by, do you know what a dense set means? Um, or a nowhere dense set means?
No, sir.
Okay, so then leave it, leave it. We are veering off into a different topic. But anyway, like I defined it for a finite set, right? You could also define it uh, for an infinite set, for
Okay.
an infinite set, a space, and you can say that uh, you can say that uh, um, this you can say that you can define sparsity by saying that this set omega prime uh, is a set of very small area. Okay, by very small area I mean the area is 0. But let's not go into that. Okay. Okay, so you understand what I mean by a sparse
Yeah,
probability
yeah,
space.
yeah, little.
Now, right. So if I have a sparse probability space, then uh, then is it possible that I start to represent each string by some number? Okay. So uh, so let's say um, so let's say, so what is the set of all possible strings of size less than equal to 10? I won't repeat size less than equal to 10. You have to assume every time I'm talking about size less than equal to 10. Okay. So now what are the set of all possible strings of size less than equal to 10? It is this quantity, right? Now I ask this question like, is it possible that I assign a number to every string? So what I want is I want a function h that takes, so denote the set of all possible strings of size less than equal to 10 as some s. Uh, so I want a function h that takes s and gives me some kind of a number. Let's just say it gives me a real number, or not a real number. Let's say it gives me a natural. Okay. So now notice that um, so if this right. So we want, so essentially this is called a hash function. This age will be called a hash function. So I want a number to represent
So
my
right,
set
it
x.
assigns numerical values to non-numerical data.
Correct.
Is it
So this
correct,
is a
sir?
non-numerical data. This is a non-numerical
See,
data.
S is actually the set of all strings, actually words that are less than or equal to 10. So
Yeah,
H represents, it takes strings to natural numbers.
correct. Correct. It will take
Okay.
strings to natural
So
numbers.
it's
So
nothing but
essentially,
random variable.
okay. So
There
what
again, we are
is
assigning numerical values to non-numerical outcomes only, sir.
true? True,
It's
right?
most both are
So the
similar.
question is true. Good question. So um, is age a random variable? So you have to understand that when we are um, when we talk about of a random variable,
Say,
uh,
talk little louder, sir.
whatever the space that
It's
we.
breaking now in between.
Hello, can you hear me?
Yeah,
Oh, okay. It's
talk
probably
little
due to my.
louder, sir. It's breaking in between.
Okay, okay. Yeah. So when you talk of a random variable, it's not enough to just talk about um a function. A random variable is something uh, that acts on a measure space. Okay, it has to act on a probability space. Okay, so right now I have this set S of of strings, but I have not defined a probability space on it. So if there is if I know that there is some probability to S or a probability measure which is defined on S, let's call it mu, and
Okay, understood now, sir.
if you
Okay,
have a
okay.
function,
Okay, that is it.
yeah,
Okay, I
correct.
understood the difference
Then
between
each
this.
then you can
Okay.
consider,
There,
yeah, then you
okay,
can consider
there,
H to be.
yes contains only probability functions. Okay, okay, that's all. Clear, sir.
Hmm.
But it is
Okay,
similar to
okay.
that only.
It is similar. It is
Yeah,
similar. I
similar
agree.
to
It is
that
similar.
only.
Yeah, yeah, yeah. So now essentially, what you want is so what happens is that you can represent each string by a number. Okay. You also want certain properties of your hash function. So you want that if S1 okay. So now let's consider a subset S prime, um, or let's consider a subset W. Okay. So let's define what is W. W is a subset of S. It is the subset of valid words of length uh, less than equal to 10. So W is my set of valid words.
Okay.
Um, so I want my hash function to be such that uh, so this is a desirable property that if you give me two elements W1 and W2 that belong to W. So essentially, if you give me two valid words W1 and W2, then H of W1 uh, should not be equal to H of W2 if W1 is not equal to W2. This is a desirable property. Okay. If or another way to formulate it is if W1 is not equal to W2, then probability that H of W1 is equal to H of W2 is small. Now you can ask, okay, how did probability come into the picture? H is a H is age is just one function, but how did probability come into the picture? Okay, but let's assume that age itself is a set of all possible functions um, from. Okay, uh, so so this is a desirable property of hashings. So the main advantage of hashing is that you can you can you can store a lot of these non you can store a lot of these numbers or you can store these non-numeric information in the form of numbers, and that has a lot of benefits or a lot of advantages. um, so with that in mind, this is like a brief introduction to hashing. If you want to understand more about hashing, then the book that I would suggest is Corman, Introduction to Data Structures and Algorithms, by Corman. Um,
Okay. Okay, sir.
so
Thank
this
you.
has an entire chapter on hashing and hashing techniques and what is a good hashing scheme and all that stuff. Okay.
Okay.
Um, so now let's look at some of the problems. I think there are two problems that they have given related to hashing. So let's
Okay.
look at problem number two first. Okay. Um, okay. So here there is one hashing scheme that is defined. It's called pairwise independent hashing. So what you do in pairwise independent hashing is that if you have two elements x and x prime, uh, um, then let's say so let's say S is my data set, and I want to map it to some other representation, which is um, some numbers, let's say. So T is a subset of of the set of natural numbers. Okay. Now in pairwise independent hashing, what is essentially is being done is that for each element x in S, you pick a random number from T and you send x to that number. Okay. Again, for x prime, you pick another random number in T and you send it to that number. Okay. Um, yeah. So, so if I ask, what is the probability that uh, that two numbers x and x prime are sent to the same number, which is this question, um, then it's equal to 1 by mod t, right? Because let's say you have sent x to one of the numbers, x prime can be sent to uh, all the other numbers of t with equal probability. So the probability that it lands with exactly the same number for which you have assigned to x is going to be 1 by mod t. So this is the correct answer for this problem. Okay. Um, right. Again, if you take this first example, so so here what you have is you have the space S is 20-bit binary strings, and you are hashing it to a space of 10-bit binary strings. Okay. So you can ask the question, what is the benefit of hashing? Okay. The benefit of hashing is you can represent something with less amount of information. So let's say I have 20-bit strings, and if I can represent a 20-bit string with a 10-bit string, then I have essentially found a representation, a smaller representation of it. But the question is, the representation has to be unique. Like if two strings S1 and S2 are given the same number, then it's not good, right? So you have to find an injective map. Okay. But the question is, finding these injective maps can be hard in practice. So um, so very often, what happens is that if you have a 20-bit binary string, so what the set of all possible 20-bit binary strings is 0, 1 to the power 20, which means 0, 1 cross 0, 1 up to 20, right? Uh, but typically, I think there's some noise coming. Can you mute your
Yeah, sir. Is this one is last option? It's 1 by 2 power 10. It's my guess
huh?
only. Is this the last option? Correct.
Then which of the following is true for pairwise independent? Yeah. So the probability that they land up in the same one is 1 by 2 to the power 10.
Previous
That's right.
problems
Yes, it's the
concept
same.
only, no?
Correct.
Yeah, 1 by 2
Correct.
power
Correct.
10.
Correct. Yes, that's
Is
correct.
it right,
That's
sir?
correct. No, I want. Huh. You are right. You are right. You are right.
Okay,
Um.
thank you.
Okay. So now let's look at a somewhat different question. Um. Because it's yeah. Um. Just give me a second. I'll bring it up. Okay. So let's take the problem number four first. Okay. So in problem number four, yeah. So in problem number four, uh, do you understand what a graph is? Like combinatorially, what a graph means?
I didn't get your point. Graph, I know, sir. Hamiltonian path, I know all these things.
Ah, okay, okay, okay. Nice, nice, nice. Yeah, this is a question related to that only. Okay, so here what is happening is that there is a tournament that is happening with 8 teams. So n equals 8 teams are playing this tournament, and so and with this you are forming a graph T, which is called this tournament graph, where the vertices are the numbers from 1 to
1
n.
to 8.
Yeah, yeah. I'm just going to call it 8 because it's easier rather
Vertices
than
of the
calling
graph.
8. So this is the vertices of the graph, and
Yeah.
the edges. So the edges. So the edge is a directed set. I mean, not a directed set. The edge is a. These are directed edges. It's a directed graph. So an edge. Uh, so an edge I comma j exists. So okay. Let's say an edge I comma j such that uh, I has I has been beaten by J. So if you read the question, he says we can define a directed Hamiltonian graph where each team corresponds to a vertex. There is a directed edge from x to y if y beats x. So if I has been beaten by J, then there
Oh,
is an
there.
edge.
Okay, okay. X
Yes,
beats. Okay, okay.
right. So now Hamiltonian path is defined in this way.
Yeah, Hamilton path is a path, it connects all the vertices of the graph exactly once.
Correct, correct. So a Hamiltonian path is a sequence um, of
Up to that 8
it's
vertices.
basically a path x1 to xn
Yeah.
where where x1 to xn is a permutation of 1 to n, and the edge xi comma xi plus 1 belongs to E where I is less than n greater than equal to 1. Okay, so this is how the Hamiltonian path is
Okay.
defined. Um, so now they're saying suppose IPL is organized fairly and all teams are balanced to ensure that in every match both teams have equal chance of winning, which means that uh, uh,
They have
which
equal
means that
probability.
yes. So which means that the probability that the edge ij occurs is equal to the probability that the edge ji occurs, and
Okay.
that is equal to half. So so you could have this or you could have this with equal probability. Okay. Now, given any sequence of 8 teams, what is the probability that the sequence forms a Hamiltonian path in T? So which means that if I give you if I give you a random sequence of vertices x1 to xn, what is the probability that this permutation pi is a Hamiltonian path? So this is easy to answer, right? Why? If pi is a Hamiltonian path, then that means that you have the sequence of vertices x1 to x2 up to xn minus 1 to xn, right? Now the edge x1 to x2 uh, can occur with half probability. The next edge
Half.
x2 from x3 also occurs with half probability. Like this, you have n minus 1 such edges. So the answer is 1 by 2 raised to the
1
power
by
n
2
minus.
per 8. N
Yeah,
minus
1 by 2 n minus 1. So 8 is n is 8. So 1 by 2 power 7. 1 by 2 power 7 is 1 by 128. So that is the answer. Okay.
Is it not 1
Right.
by 2 per 8, sir? 7.
No, why is it 1 by 2 power 8? How many edges do you need? So you have x1, x2, x2, x3, all the way till x7,
Okay, okay,
x8.
okay, okay, sir. Okay, okay, okay.
So it's
Thank
1
you.
by 2
Sorry.
to the power 7.
Okay,
Okay.
okay,
Okay. So it's 1 by 128.
okay.
So so we know this nice fact now. So probability that pi is a Hamiltonian path is equal to 1 by 2 raised to the power
Oh,
n minus
2
1.
per n minus. It's 1 by 2 per 7.
Yeah, 1 by 2 power 7.
7. Okay.
Now I'm going to use this information in this next problem. And this is a very nice problem. It's very commonly used in in uh, uh, in problems in combinatorics and in lots of other discrete algorithms where where you answer something using a probabilistic technique. Okay. And uh, like like in a place where you would seem that there is no probability over there, but still a probabilistic technique gets useful there. So so the broad idea is what I would summarize as counting two ways. Okay, if I give you a set of if I give you a finite set and I ask you to count that set, count the number of elements in that set, then um, then uh, then however you count the number of elements in the set, you will always arrive at the same number. Okay. So what the probabilistic technique gives us is that it gives you an alternative way to count the number of elements in a set. It allows you to make certain quantitative statements on the number of elements in the set and so on. Um, and that basically allows us to estimate the number of elements in that set. So let's see how that gets useful over here. So the question is this. Let's continue the previous question. Consider all possible distinct tournament graphs on 8 vertices. Okay. So you have uh, you consider the set of all possible uh, um, consider the set of all possible tournament graphs that are possible. Okay. Um, so can you tell me uh, how many such tournament graphs exist? I'm not asking the question. This is a quick question that I'm just asking. How many such tournament graphs can exist if I consider all possible?
What's the question, sir? I didn't get you.
The question is, we defined a tournament graph in this problem, right?
Yeah.
So you have an edge from I to j if I has been defeated by j. Now, if I ask you, uh, what are the number of all possible tournament graphs?
Talk all possible tournament graphs. Is it 8C2?
It's 2 to the power 8 C2. It's 2 to the
2 to
power
the
8
power?
C2. 2 raised to the power 8 C2. Why?
Why we are using
So let's,
two raise power?
yeah. So let's ask this question. What is the number of tournament graphs? Right. So a tournament graph has so what is the set of edges of uh, the
The
tournament
game
graph?
between
So
two teams
it's number
actually.
of pairs I comma j. It's the number of pairs I comma j, where I is not equal to j.
J.
Okay.
Yes.
But the pair I comma j, if I comma j exists, then j comma I does not exist, right? So I mean, there are two possibilities. Either I has been defeated by j, or j has been defeated by I. If j has been, so essentially,
If
if
both
you have
are,
the two
I
vertices
means
I
it
and j,
represents one team, sir. Both are
yeah,
same
I
only, sir. I is not
represents
equal
one
to
team, j
J.
represents, yeah, I is not equal to j. So I is I is one team, j is another team. Now there's an edge between I and j. Now either the edge
Yeah, there is
is
okay. There
in
is
this
only one
direction
edge
or in
between
the
I
other
and
direction.
J.
There's only one edge between, and either it is in this direction or the other direction. So there are two directions possible. Okay. And what are the number of all possible edges? The number of all possible
Why
edges is
two
8
directions,
C2.
sir? See, they are
No, I
actually
mean,
playing games now, sir.
what is
The tournament between two
I'm
teams
asking you,
only.
what is the set of all possible outcomes? I'm asking you to enumerate the set of all possible outcomes. If I'm enumerating the set of all possible outcomes, so then what happens? In one such outcome, I is defeated by j. In another outcome, j is defeated by I. And in likewise, I'm asking you to construct the set of all possible tournament graphs,
Okay, okay,
where you
okay,
consider
okay,
all
okay,
possibilities.
okay,
So
okay,
here
okay.
you have eight C2 edges, and there are two
It's
possibilities exist. Either I
eight
is,
C2. Okay.
it's 2
It's 2
raised to the
power
power
8,
8
8
C2.
C2.
Yeah.
For this
So this is
question,
the
none
total
of the above is the
number of,
answer.
huh?
For this question, none
What?
of the above is the answer only, no.
No. Both of the above is the answer. But yeah, I've not even read the question. So let's first read the question. So suppose every year a new season is played until all the tournament graphs on 8 C2 vertices are exhausted. Okay, you don't have to worry about this line. Further, suppose that every season of IPL is fair, that is both teams have equal chance of winning in every match uh, of each season. Okay, then which of the following is true? Okay, now let's not look at the hint. Okay, let's not look at the hint. Let's read the options first. So the first option is there exists an IPL season for which its tournament graph has at least 8 factorial by 2 to the power of 7 Hamiltonian paths. Is this option correct or incorrect? Okay, if you do not read the hint, if you read just up to this, and I ask you to make a statement that I can find at least one tournament graph. So that means there is at least one such graph that is formed where there is at least 8 factorial by 2 to the power 7 Hamiltonian paths. It's hard to answer
Okay,
this
I
question, right?
checked that, but second option is correct. But here
Yeah, second
options
option is
both of
correct.
the above or none of the above, so that's why I said none of the above. Okay, I'll calculate the first one, sir. Okay, I'll check the first one.
Uh-huh. This is correct, obviously. No, the first option is the interesting is the entire reason why we use probabilistic techniques in counting. So here, so this course, this probability for computer science is not just about probabilities. It also shows how probability can be used in counting stuff. So this is one example where you can do it. It's very difficult to answer this question because it's a problem in graph theory, where if I tell you, oh, I consider the set of all possible complete graphs, complete directed graphs, where I put an edge between where you are allowed, where you are given two choices. Either you put an edge between I and j, either the edge between I and j is pointing in this direction or in the opposite direction. However you want to put it, you put it. And in this way, you construct this complete graph. And then I ask you that show that there must exist one graph, at least one graph, where there is at least 8 factorial by 2 to the power 7 Hamiltonian parts in it. Um, this is very difficult to answer just by it.
It's not
But let's
purely
see how.
probability. Probability with
It's a graph theory
combinatorics,
problem.
probability with
Yes, it's
graph
a problem
theory.
in graph
Okay.
theory, but you are going to use combinatorics to answer it. So, but you're going to use probability to answer it. So let's see how we can use probability to answer it. Okay. So the question is, let's first state a fact. Okay, let's state a fact. Uh, if x is a if x is a random variable, so let's say x is a random variable which takes values in some 1 to n with equal probability. Okay, let's not write 1 to n. This is slightly incorrect. Uh, so it takes values in some set a1, a2 up to some an. Okay, and it takes these values with equal probability. So the probability that uh, x equals ai is equal to 1 by n for all I. Okay. So then the expectation of x, whatever the expectation of x is equal to a1 plus up to an by n.
So these things I know, sir. No need, don't waste your precious time. I know, sir.
Yeah, yeah, yeah. No, let me build up
So
to
you
the
want
theory.
to
So
say something?
whatever this, what, yeah. So whatever this
Okay,
expectation
okay. Then you
is, let's
proceed,
call
sir.
it mu.
Yeah,
Whatever this
news.
expectation is, let's call it mu.
Okay.
Well, uh, it means that so whatever the expectation of a random variable is, it means that x must attain mu. There, there has to be, or in other words, it means that uh, one of one of the AIs must be greater than or equal to mu. Because if all the AIs were less than or equal to mu, then because if all the AIs were smaller than mu, then the mean would also be smaller than mu. So if the mean is bigger than mu, or the mean is equal to mu, then one of these elements, a1 to an, must be at least equal to mu. This is a easy fact. Okay.
Okay.
So now let's count. So let's count uh, the number of Hamiltonian paths in a graph, in a tournament graph, in probability. Sorry, not in probability, in expectation. So whenever you see these counting type of problems and in expectation, it's good to start thinking in terms of indicator random variables. So you define an indicator random variable called x pi. Okay, where x pi, what is pi? So pi is a permutation. Pi is a permutation uh, of 1 to n. Here n is equal to 8. Okay. So you define a random variable x pi, where x pi is equal to 1 if pi is a Hamiltonian path and 0 otherwise. So if so here we're considering the space of all possible tournament graphs. So every tournament graph occurs with equal probability. So if I pick a random so if I pick a tournament graph uh, uh, randomly, then what is the probability that x pi is equal to 1? That is, what is the probability that this is a Hamiltonian path? We saw in the previous example that this is equal to 2 to the power n minus 1, which is 1 by 2 to the power 7. Correct? Now,
Yes. Okay.
so if I have any tournament graph, and if I ask you what are the number of Hamiltonian parts in it, so you can say that the number of Hamiltonian parts in it is equal to sum over of x pi, where pi varies over the permutations of 1 to n. So the set of permutations of 1 to n, uh, the, let's just write it as omega n. So omega n is the number is the permutations of.
It's actually 8 factorial.
Yeah, it's actually 8 factorial. It's 1 by n. So it's actually, let's write it as
If it
5.
has n numbers, it is n factorial.
Yeah. So the so the number of Hamiltonian paths in any graph is equal to sum over of this quantity. Now let's call it a random variable. Let's call it like h. H is a random variable. H counts the number of Hamiltonian paths in a graph. So what is the expectation of H? Expectation of H is equal to sum over of expectation of x pi.
8
That is equal to, that is, so how many permutations are there? There are 8 factorial
8
permutations.
factorial.
And
Okay.
what is the expectation of x pi? Expectation of x pi is equal to 1 by 2 to the power 7.
To 7. Okay.
So that means that expectation of h is equal to 8 factorial by 2 to the power 7.
Oh,
That means, there must exist a tournament graph T where the number of Hamiltonian paths in T is greater than or equal to 8 factorial by 2 to the power 7. Okay.
okay, sir. It's clear now.
Yeah. You can see how powerful this technique is, right? It's a very
Okay,
powerful
okay.
technique. Okay. That's all I had.
Okay, sir.
Uh,
Thank you. Thank you for teaching me alone. Okay.
yeah, yeah,
Thank
yeah,
you
yeah.
very much. Thanks a lot.
Yeah, yeah, no problem. So, so on Friday, this Friday, which is the last,
Yeah, I remember that.
yeah. So I am going to conduct a special session on Wednesday. And
Better you put a mail, sir. Then few people will join.
yeah, yeah, I'll ask NPTL. So I've already filled I've already let them know, but it depends on them how, when they will broadcast this information. Um, this Friday, I do not know if I'll be able to conduct the session. I have some very tight deadlines next week on Monday and Tuesday. Maybe on Tuesday, I'll conduct week 8, which is the last week of the course, and on Wednesday I can conduct the extra session. Um,
Okay.
so maybe not on Friday. I'll send a note to the students. Um, I'll basically, I don't get to send the note. I'll ask them to send the note. Like
Okay.
NPTEL will send the note themselves.
Okay.
Yeah. All right.
Okay.
Thank you for joining.
Thank you, sir. Thank you. Thank you for teaching me. Okay. Thank you. Thank you very
Bye.
much. Thank you.
Thank you.